here will tell us about P4-SpecTec, language mechanization for P4.
So thank you for the introduction. Today I'll be talking about P4-SpecTec, a language mechanization framework for P4. And today, just this morning, I realized that this has a little bit different flavor than the other talks. So I'll be talking about types, but it's more focused into the language specification aspects. One moment. Let me just try it again. Yes, so our project title can be naturally decomposed into two components, P4 and SpecTec. P4 is a domain-specific language for the networking domain, and SpecTec is a language mechanization framework. And put together, our main objective is to adopt language mechanization approach into the P4 language. And this talk will be organized along three main questions. First of all, what is mechanization and why do we need it for the P4 language? Understanding the necessities, we'll discuss how to mechanize the P4 language definition using P4-SpecTec. And finally, what are the benefits that P4-SpecTec can deliver to the P4 ecosystem? But before getting any further, let me very briefly explain about the P4 language. P4 is an acronym for Programming Protocol Independent Packet Processors. It is a domain-specific language for programming network devices like switches and routers, telling them how to take in an input packet, process it, and output that along the network path. But for the sake of this presentation, it is just enough to know that P4 is statically typed, so we would need a type checker. And also, a large part of the language semantics is imperative, like the C programming language. Now, viewing P4 from a programming language point of view, we identify four main representations of its syntax and semantics: the official spec, implementations, tests, and formalizations. The official P4 spec is an informal prose description of the syntax and semantics of P4. And there are also implementations, for example, the P4C reference compiler in C++, which is an executable representation of the language. The reference compiler also comes with a test suite demonstrating the behavior of P4 with input-output examples. And last but not least, we have formalizations, usually found in academia, giving precise mathematical description of the language. And the presence of multiple representation invites us to the question, are the four representations truly in sync? In other words, are they consistent in defining the syntax and semantics of P4? Of course, in principle, they should be. However, in practice, they are not. The main reason is that the four representations are maintained by different parties, and they evolve at different paces. And what contributes more to this inconsistency problem is that the language itself is evolving. For example, the official spec introduced generic types as of May 2021. However, this spec update did not land perfectly on existing implementation, where the P4C reference compiler emitted an error when this new feature interacted with yet another language feature, which is type inference. This bug was only identified and patched March this year, which is very long after the spec update. And for formalizations, they exist, but however, they remain frozen before 2021, while the most recent version is based on 2024. And this kind of inconsistency is undesirable because it can lead language designers, developers, and hardware vendors into diverging directions. So this inconsistency problem boils down to this core question. Can we at the same time evolve a programming language while maintaining the consistency between the representations? Then again, from a programming language perspective, we claim that the answer is yes. There is a single source of truth that underlies all the different language representations, which we call the specification model. This refers to a complete and an unambiguous definition of a language. For example, it can be a complete formalization or a definitional interpreter. And once we have the spec model in hand, we can view other representations as instances of the spec model in different medium. For the spec document, we can view it as a verbose version of the spec model. And we can also implement the spec model in terms of programming languages to get implementations. Then, language mechanization frameworks allow us to systematically define the spec model. It comes with a domain-specific language called a meta language for defining the spec model. And because the spec itself is written in a DSL, we can parse the specification and apply various automated manipulation on the spec. Then, language mechanization frameworks can automatically derive various backend representations starting from the specification model. So this can solve the inconsistency problem while allowing the spec model to evolve. So far, we've discussed what mechanization is and why we need it for P4. And let's dive into the detail and see how we can mechanize the P4 language definition using P4-SpecTec. And one good strategy here is to look at what other languages are doing. In fact, the inconsistency problem is not specific to P4, but it is prevalent among many other programming languages, for example, WebAssembly or Wasm in short. And for Wasm, and language mechanization framework has been successfully landed into their official spec authoring toolchain. Wasm-SpecTec is now the official specification authoring toolchain for WebAssembly, where it automatically generates a specification document as well as a Wasm interpreter starting from the Wasm specification model. And let's now see how this works in detail. This is a portion of the WebAssembly official standard defining the dynamic semantics of Wasm if instruction semantics. The spec is interesting in providing a dual representation of the semantics. Below, we see the formal specification defining the dynamic semantics in formal reduction rules. So this reduction rule reads, on an abstract stack machine, if we are given a Wasm if instruction, and if the top of the stack is a non-zero constant, integer constant, then we would evaluate the then branch. And otherwise, then we would reduce to the else branch. And we also have the prose specification above, giving a step-by-step pseudocode style explanation of how to compute the reduction semantics. The formal spec is crisp, yet the prose spec gives a more kinder explanation, which is accessible to a broader audience of the specification. And these two styles of spec, although in different formats, should essentially describe the same thing, the Wasm dynamic semantics. And of these two models, Wasm-SpecTec chooses the formal spec as their spec model. So they come with a meta language that is designed to very closely resemble the textbook-style formalizations in ASCII characters. Below, we see the mechanized spec model in Wasm-SpecTec for the dynamic semantics of if instruction. And we can see that it very closely resembles the formal specification above. Then from the specification model, Wasm-SpecTec automatically generates the prose specification. At a high level, the spec model is a collection of declarative reduction rules saying what the semantics of Wasm is. However, it does not necessarily describe how to compute the semantics. And Wasm-SpecTec somehow automatically derives the prose specification, giving algorithmic pseudocode of how to carry out the reduction in a computational sense. And this conversion from a declarative form to an algorithmic form is non-trivial in general. However, Wasm-SpecTec manages to handle this by assuming a shared format between the declarative rules, which is reduction on an abstract stack machine. Using this baked-in knowledge, it converts the left-hand side into pop something from the stack, premises into let bindings or if conditions, and finally the right-hand side into push something back into the stack, prose instructions. Once we have the prose algorithms, we can also think of executing the prose algorithms. The converted prose algorithms as a whole describe the Wasm dynamic semantics, and if we can get to run the algorithms, then we would essentially run the Wasm semantics, essentially yielding a Wasm interpreter as a result. So Wasm-SpecTec has a prose interpreter that can run the prose algorithms, which, given a Wasm program, would compute the semantics as told by the specification, thereby deriving the correct result. And with these, Wasm-SpecTec has been now integrated into the WebAssembly specification authoring toolchain, by the WebAssembly community group this year. And now using Wasm-SpecTec, now specification designers would edit the specification model using the Wasm-SpecTec meta language. And then Wasm-SpecTec would automatically derive the spec document as well as an interpreter conforming to the spec automatically. And with their success story, we discovered that the underlying recipe for their success was the existence of an authoritative spec model. The existence of the formal Wasm standard was the starting point for the design of Wasm-SpecTec to have a meta language that closely resembles the formal reduction rules. So the underlying recipe is the driver for the mechanization framework design. And now let's resume our discussion of P4. Resuming to P4, we face a fundamental challenge that P4 lacks an authoritative spec model today. Recall the 4 representations. The official spec is there, however, it is informal and not systematic. We have the P4C reference compiler implementation, however, it takes a nanopass compiler architecture where it fails to give a monolithic view of the language semantics. Tests are naturally incomplete, and formalization, they exist, however, they are incomplete and also not up to date. However, on the flip side, this means that we have an opportunity to build a clean slate P4 specification model from the bottom up. And we can think of reusing the Wasm-SpecTec meta language to define the P4 spec model as well. The WebAssembly Wasm-SpecTec spec model is based on declarative reduction rules, or in a more abstract way, we can see them as declarative inference rules. This model excels in abstraction, hiding various implementation level details such as memory management and explicit error handling. However, it does come at a cost that the inference rules themselves are not directly executable. Wasm-SpecTec partly solved this problem by assuming a shared format between the declarative reduction rules. However, it fails to handle the static semantics to automatically derive the type checker. Take this transitivity rule, for example. To claim that type A is a subtype of type C, we have to somehow find the intermediate type B. However, this inference rule by itself does not lay out the clue of how to compute the value of type B. So type B is existential here. And because of this reason, although the Wasm static semantics is already mechanized in Wasm-SpecTec, Wasm-SpecTec fails to generate a type checker from this. So in summary, declarative inference rules are abstract, but they come at a cost that they are not directly executable. And for P4, we propose algorithmic inference rules as a model. And we define it as a subset of inference rules that are constructive, thereby allowing them to be directly executable. And to accomplish this goal, we adopt the Wasm-SpecTec meta language, but we impose several constraints to the meta language to truly ensure that the inference rules are computable. So now let's see how we mechanize the P4 language definition. This is part of the P4 official standard defining the if statement syntax and semantics. It says it uses standard syntax and semantics found in many other programming languages, but it poses a single constraint that the conditional expression must be a Boolean type. And this is how we mechanize that using P4-SpecTec. On the left, we define the mechanized P4 syntax using a BNF notation. And here we say that a single variant of the P4 statement is an if statement. And on the right, we define the algorithmic typing rule. On the top, we have a relation statement OK, which is basically a type signature for the inference rules. This reads, under a context, we will type check a P4 statement to yield an updated context. And below, we define an inference rule for the P4 if statement. Now this reads, under a typing context C, we will be given a P4 if statement. Then we will first type check the expression, get its type. Second, check that it has Boolean type. And then type check both branches. And finally, we will say that the result of the typing is an updated context CRES. And what just happened is that we just intuitively executed the inference rules ourselves. With intuitive sense, we somehow knew that the subject of the rule is the typing context C and the P4 if statement, and the result of the inference rule is CRES. Also, while reading the algorithmic inference rule with our intuition, we somehow the computation and data has flown through the input throughout the premises in order and finally to the result. So again, we have intuitively executed the inference rules. Aligning with our intuitive interpretation, we impose several constraints on our meta language to enforce computability. The first constraint is that relations in P4-SpecTec must have inputs and outputs. This is in contrast with general inference rules where they do not have designated inputs and outputs. Here we put a hint next to the statement OK declaration saying that the 0th and the 1st components must be the input of this inference rule. And with this information, we will now track down the known variables throughout the inference rules to enforce explicit data flow. And at this point, we know 4 variables, C, statement T, statement F, and expression C. And then we will check the premises in order. This is, again, a departure from general inference rules where premises can be unordered. And in the first premise, by calling a relation expression OK, we will bind a new variable type C from the known variable C and expression C. And the next constraint is that we disallow unknown variables except for binding positions. So for example, say we put an unknown variable expression sum at the input site of the relation being invoked. P4-SpecTec would reject this spec model because the data flow here is unclear. So by this, we are essentially forbidding existential premises from appearing in our specification. And the next constraint is that moving on to the next premise, we see a if x equals y type of premise. And here notice that the equal symbol here is overloaded. It can mean either an equality check, a binding from left-hand side to right-hand side, or vice versa. We disambiguate the equal symbol by consulting the known variables. If both sides are known, it must be an equality comparison. And if one side is known while the other side is not, it must be an assignment. And all the other cases are rejected because the data flow is unclear. For this case, because we know type C and bool is a terminal symbol, we interpret this as an equality comparison. Moving on to the next 2 premises, we will bind the CT and CF using the same principles before. And in the final premise, because we know C, however we don't know C-res, we interpret this as an assignment from C to C-res. And given all that premises hold, we will conclude that the statement is well typed and the updated context is C-res. So these are the core constraints on the P4-SpecTec meta language that we enforced to guarantee that the specification model is executable. Given a P4-Spec model, P4-SpecTec statically validates that all these constraints hold, thereby allowing the algorithmic inference rules to be executed. And using algorithmic inference rules, we have defined the full P4 specification model covering its syntax and the type system. And this spans about 8,000 lines of code in our meta language. Now, as a final bit, I will briefly discuss the benefits that can be delivered by P4-SpecTec. This is the vision and also the current status of P4-SpecTec. From the mechanized P4 specification model, we would like to derive all of these kinds of backends. And those in green are already worked on and are functioning to a certain level. And those in red are left for the near future. So let's start with our type checker backend. We have defined the full P4 type system using our algorithmic inference rules. And because algorithmic inference rules are executable by having a meta-language interpreter with the P4-Spec model, we can essentially yield a P4 type checker as a result, just as we did with the Wasm interpreter backend in Wasm-SpecTec. We validated our type checker backend with existing tests in the P4C reference compiler. And for the positive test checking that ill-typed programs are accepted, it passes more than 99%. And on the flip side, for the negative test checking that ill-typed programs are rejected, it passes more than 98%. And we also do have a test generation backend specialized for negative type checker tests. So we are generating deliberately ill-typed programs to uncover various type errors that can occur in the type system. While we do not discuss the details of the test generation strategy, by our test generation backend, we added 248 negative tests to the P4C reference compiler's test suite, which tests previously untested type errors in the type system. And also, with the generated tests, we discovered 26 previously unknown bugs in the P4C compiler frontend, even including soundness bugs where the compiler erroneously accepted ill-typed programs. In the final backend, we have the algorithmic inference rule, and we can render them in terms of prose and also in terms of HTML markdown. And after rendering, we get a result like in the below figure, where we have a human readable document, and also notice that it follows our intuitive interpretation of the algorithmic inference rules, yet in a more kinder interface than the algorithmic inference rule itself. With P4-SpecTec, this is how we envision the spec maintenance workflow of P4. Every time we want to edit the spec, we would edit the mechanized specification, and it would derive a parser, type checker, interpreter backend immediately, giving assurance that it doesn't break the existing tests. Also, we can auto-generate tests from the P4-spec model demonstrating the effect of the spec edits. And finally, it will also give an official specification document that is updated in correspondence to the spec edits. So with these, we are currently sharing our progress and also collecting feedback from the P4 language design working group. And our goal would be to adopt P4-SpecTec into the specification toolchain someday in the near future. So thank you for your attention, and I'd be happy to take questions.
Here, so if you have any, please come to the mic.
Hi, thanks for the talk. Is there a concern with this kind of thing that if you have a new version of P4 that adds some new features, you would have to go and sort of expand on the SpecTec language to fit them in? I guess, how general is the language? You sort of tailored it to fit P4 as it exists now, but if you made P4 different in the future, maybe this is a problem for WebAssembly too, I don't know, would you have to sort of first work to generalize the SpecTec language to fit the new features?
I see. So I think that's an open-ended question because we don't know the spec updates to come beforehand. Mm-hmm. But however, I view P4-SpecTec as a slight variant of the ML family. So I think it is quite general, but we might think of adding more type annotations and more syntactic sugar to make it feasible to make it easier to implement new features in the language.
Okay, thanks.
So, well, one other feature of P4 of which I'm aware, apart from the ones you mentioned at the start, is that P4, or at least most versions of P4, don't contain loops. Are there any optimizations or shortcuts you can use for P4-SpecTec that take advantage of that fact that wouldn't be possible for a more general programming language?
I think that would make sense if we would start to make a verifier backend for P4 using P4-SpecTec, and in that case, it would definitely be beneficial that P4 doesn't have loop. But for now, we are just dealing with the semantics itself, but not manipulating the semantics in a more advanced way. So that, at the current state, does not prove any benefit at this level.
Thank you.
Okay, can we have the next speaker set up? And then I have a quick question while we get transitioned. So I'm just curious. You didn't pass 100% of the tests. There were a few that weren't passing. Is that a problem with the spec or with the tests?
Well, it's kind of both. We have problems with the specification. We haven't dealt with very specific features of P4 yet. And also, we have some implementation issues. We have to deal with large size integer literals. We model with the OCaml bigint library, which just miserably just happens to be a timeout. So we have to deal with them